Hey, welcome back. In this video, we're going to continue the conversation of applying Taylor series in different applications. This first example actually is a lot like examples we've done in the past, where we're going to use previous Taylor series representations to develop a representation for a certain function. But then you'll see next, we're going to use some tricks and kind of going in the opposite direction and identifying a series and then being able to evaluate an exact value for that series given its similarity or exactness after manipulation to one of our Taylor series representations. In this first example here, we're being asked to find the Maclaurin series for the hyperbolic sine. If you haven't seen this much, it's probably not a big deal in your life right now. I won't talk much about the hyperbolic sine in detail, but it has important applications that you'll see throughout mathematics and physics. Just to say, it's a sine. We have a cosine version also, and they're based off the hyperbola, not the circle like normal sine and cosine. And there is this concept of hyperbolic geometry that they're very important for. For us, it's just really interesting in how they interact, and they act a lot like our normal sine and cosine that are based on the unit circle. But I digress. This is actually the representation I'm going to give is often one of these common ones that you'll see on these tables. So this is the definition of the hyperbolic sine. But importantly here, I'm going to rewrite this just to make it easier on my life as 1/2 times e to the x minus e to the negative x. And what I'm going to do, okay, to represent this is I'm going to replace the e to the x and the e to the negative x with the Taylor series representations. The only trick I need to do is use composition here and throw a negative x in here, which will actually make this an alternating series. And you'll see how I put these together. I'll throw that negative in here and then throw this in below. So let's give ourselves some space here and come over here. So if we do that, we have a 1/2, and then this Taylor series for e to the x is just the summation from k equals 0 to infinity of x to the k over k factorial. And then we're going to subtract the sum from k equals 0 to infinity of simply negative x to the k over k factorial. And since I don't want to rewrite this all again, I'm going to erase this and just separate the 1 to the k and the x to the k, just so it's very clear to me there's this alternating going on. And then what I'm going to do, just because I think it clarifies the next step, is I'm actually going to put these two power series together. And I know I'm allowed to do that if they're both on the same interval of convergence, which they are from negative infinity to infinity. The composition of that negative x does not change that right here. I can combine these, and so what I get is 1/2, and then I get the sum from k equals 0 to infinity. And then now, the way I'm going to think about this, which I think is really helpful here, is I'm going to think about this as one term together. Oh, I lost my little k up there, I notice now. That gives the alternation over k factorial. And now importantly, what I'm going to do is make a quick analysis of these terms right here. So I'll just label this right here, these a sub k's. And importantly, when I'm looking at this, I know that when k is even, this factor right here of -1 to the k will end up being a +1. Which means this will actually have no effect, and it will be x to the k over k factorial minus the exact same thing. So in the case when k is even, I know that this a to the k, this kth term of this sigma sum right here, will equal 0. And then in a very similar but opposite way, when my k value is odd, what I'll get in this case is a -1, so I'll have a negative exponent on this alternating factor right here. And they'll turn this into an addition. So instead of canceling for the even terms, the odd terms, I'll just get a double up of this statement right here. So a to the k is going to equal 2 times x to the k over k factorial. So importantly here, and I can expand this out, and maybe I should before I write my statement, but importantly what's going on is I won't be writing anything for these k values when they're even, because I'll just get 0, and adding or subtracting 0 doesn't do anything. But when k is odd, I get these doubling ups. And again, I don't need to think deeply about when I'm going to write this expanded form, because I have done the logic right here. I know what the kth term will be for when it's even or odd. So I have 1/2 right here. So when I have k equals 0, well, 0 is even, so I leave that. When k equals 1, what it will look like is 2 times x to the 1 over 1 factorial. When it's 2, it goes away. When it's 3, I'll get 2 times x to the 3rd over 3 factorial. And let's just do a couple more. X to the 4th, that will be 0, so I don't need to add that on. And then when I get 5, I'll have plus 2 times x to the 5th over 5 factorial. And this same pattern will keep happening. Importantly here to this conversation is the fact that I have this 1/2 on the outside, but I know from this analysis right here that every term will have this factor of 2. So this was just like in a previous example when I have this infinite series, and I know something very important about each of those terms, and that pattern or that nature that I analyzed, I know has to occur in every term. This factor of 2 is the same thing, so I'll cancel the 1/2 times each of these factors in each of these terms all the way along. And then look at what I have right here. And what I have is a pretty clear series, and I just have these odd exponents divided by this odd factorial. So I can write this summation, and we'll just go from k to 0. And now what I need to do is I'm going to make the adjustment up here where I get this 2k plus 1, which as we iterate k just represents the evens, and then divided by 2k plus 1 factorial. So as I was saying at the beginning of this video, and I just think it's very interesting that when you start playing with the hyperbolic sine or hyperbolic cosine, you end up thinking, man, this is almost exactly the same as the sine function, and this is showing up in this Taylor series representation. So look at this. We didn't use the sine anywhere in this. We used this representation or the definition of the hyperbolic sine. When we generated this power series, take a look real quick about how eerily close it is to the sine power series or Taylor series right here. The only difference between them is that alternation that we get with the sine. We don't have the alternation here with the hyperbolic sine. And just to give a hint in your future work, if you're ever dealing with a power series and you're thinking, man, this is so much like the sine power series or Taylor series, except for the one I'm looking at doesn't have the alternation, think about that and consider using the hyperbolic sine. All right, in this example, we're going to show you a really cool application of using Taylor series to evaluate an infinite series. Importantly, the series I'm looking at right here is not a power series or a Taylor series. Importantly there is because I don't have this variable x. But as I'm looking at that, it looks like this is the spot where that x would be. My first thing to do when I'm looking at this is to try to figure out which of these series this somewhat represents. And I could act like I'm looking through a lot of these, but I'm looking specifically for the alternation, which is important, and this coefficient down here. I'm just trying to find something similar. This exponent is important also, but I can always make some changes and some manipulations to make different things happen. And in this case right here, I'm looking at the tangent inverse of x. This looks exactly the same as far as the alternation goes and this divisor of 2k plus 1. The only issue is the exponent that I have going on up here. And now importantly again to say, what I'm working with here is not a power series, so I'm allowed to use a bit different tricks than I've done previously. We've done more recently with the power series. I use my normal infinite series rules, but what I'm going to do, I'm going to work hard to get this exponent to look exactly like that 2k plus 1 right there. The first thing I'm going to do is I'm going to rewrite the 1/4 as 1/2 squared. So everything else will look exactly the same. So I have the summation from 0 to infinity of this alternating factor right here. And what I get now is 1/2 squared to the k minus 3 all over 2k plus 1. And now this works really beautifully and something to remember when attacking these. Since I rewrote the 1/4 as 1/2 squared, what I'm going to do now is the property of exponents and apply this 2 to each of those terms up in that exponent right there. And so I'll have the summation again from k equals 0 to infinity All this is the same. The interesting thing is what's going on here. So I'm going to have 1/2 to the 2k minus 6. Again, importantly, I distributed that 2 to both of those terms in that exponent, all over the 2k plus 1. And then I'll make my next move without rewriting this whole thing again, since I'm just doing small manipulations. But what I'm looking at is this right here. What I want to write this as is 2k plus 1 plus or minus some constant, so I can work with that 2k plus 1. And if I look at this right here, 2k minus 6, I can think of as the same thing as 2k plus 1. I'll put that in parentheses just for it so it's easier for me to visualize. So that's the same as 2k plus 1 minus 7. So if I simplify this statement right here, we would all agree those are the same. And so what I'm going to do now is just replace that 2k minus 6 with this 2k plus 1 minus 7 statement. And really the only tricky stuff here will be remembering all your exponent rules. But what I'm going to do now is I'm going to split this up, this 1/2 into the 2k plus 1 part, and then multiply that by 1/2 to the negative 7. Again, it's just a property of exponents using the multiplicative nature and adding the exponents, or subtracting the exponents, I guess, in this case. But if I have negative 1 to the k, I'll now have 1/2. And this is raised to the 2k plus 1 times 1/2 raised to the negative 7 there, all over 2k plus 1. And that's really the crazy trick right there. What I am going to do right now, and again, since I don't have a ton of room, only a little bit of room left, I'm going to pull out this factor, kind of clean stuff up here, take this 1/2 raised to the negative 7 and bring it out front of the summation. I can do that because it's just a constant factor, unaffected by the iterative variable k. And so here I've done that. I've pulled out that factor of 1/2 to the negative 7. Now importantly, I'm looking at this. This is now set up exactly like the tangent inverse. The difference is I've plugged in this 1/2 for the x, and actually then I can re-represent this with tangent inverse of 1/2 as long as this value of 1/2 is on the interval of convergence, which it is, thank God. This problem would have blown up in my face if it wasn't. So 1/2 lies on the interval from negative 1 to 1. So this right here can be represented by really the composition of the constant 1/2 being plugged in here. And so this whole sum equals 1/2 to the negative 7, which was that factor came from that adjustment I was making to that k minus 3 up there from the very beginning. And then this series right here is the tangent inverse of 1/2. So to wrap up this example and the one previously, first and foremost, whenever you have a series expression that you're trying to use a Taylor series a representation for, it's important to know what you can manipulate and what you can't manipulate. Importantly here to really emphasize, I was able to pull out this factor of 1/2 to the negative 7 because that was a constant factor that wasn't being manipulated by the value of k. And again, I pulled that out of this part right here. The tricky step was writing that 1/4 as 1/2 squared. But after that, it just had some easy manipulation to go right there. And then from this statement to this statement, I just want to clarify, we know that on the interval from negative 1 to 1, so all of those x values, the tangent inverse of that x value will be represented by this infinite series right here, but that's vice versa. In this case right here, I had exactly the same thing, except I had this 1/2 plugged in, which is on my interval of convergence. So I know that if I plugged in 1/2 in tangent inverse, it's exactly equivalent by its representative Taylor series on negative 1 to 1. And then to go back for that first example, whenever you're looking to create a Taylor series, make sure you will rely heavily on a list of known Taylor series. And again, this isn't an exhaustive list. You can find them in your textbook or in other resources online. All you're looking to do is A, make sure you obey the rules for these infinite power series, and B, replace all the non-simple expressions inside of your statement with the power series. In the first case with the hyperbolic sine, it was pretty clear we were going to use this e to the x, and then the second case we would compose negative x into that e to the x to represent the e to the negative x power series.